All right, so I guess we should start and then see if Olena or Igor joins in. Let me get back to my slides and just repeat what I said yesterday. So a couple of words before we start, before we go on to practical exercises. I just want to do a short recap on what we have discussed yesterday. So we basically talked about L2 regularization and L1 regularization for any sort of error function. Should you have MSC, RSS, BCE, whatever have you, so you can use L2 regularization term, which is just a sum of weights squared multiplied by lambda, which is a strength of the regularization. And in terms of L1 regularization, it's just a sum of absolute values of weights times lambda, which is again a strength. And we were just discussing, so when should I use one and when should I use the other one, right? So when basically I was saying that L2 regularization is what usually people use to reduce overfitting, and L1 is something that people prefer for feature selection because it's a nice feature selection method that you run as a pre-processing technique, and then you get this best performing features that you can use for your modeling. And that's what the discussion we had with Kenneth. Then I was saying that when you have a machine learning method and then you use L1 or L2 regularization, you're basically saying that I use machine learning model with L1 or L2 regularization. But when you have a specific model type, like linear regression, right, that we have discussed yesterday, and you use L1 regularization with linear regression, this is called, Simon, this is called, do you remember what was the name?
Lasso.
Lasso regularization, yeah, it was lasso regression. And Oleg, what was the name for the other one?
Not fair, because I remember L1, but don't remember L2 name.
Ah, god damn. Kenneth, do you remember the other one?
Yeah, ridge regression.
Ridge regression, yeah, ridge
Okay.
regression.
Thank you, Kenneth.
Kenneth always here, to back you up. All right, so we just discussed that LASSO is an acronym, so it's not just like made up name, it's an acronym. And the acronym stands for least absolute shrinkage and selection operator. Don't remember that. I never remember that. It's just, if you want to be fancy and you want to say somebody like, what LASSO is and, that kind of stuff, just to show off. And ridge regression is known as basically named after Tikhanov, Andrei Tikhanov, who was the guy who proposed L2 regularization ridge regression. And yeah, that's arguably one of the most popular regularization techniques in machine learning. All right. And then I asked you a question, and since we don't have anybody, I was asking question basically, so how do you call L1 or L2 regularization? Oh, sorry, this was link stuff for deep learning. And then we had this a minute of silence, and so basically nobody knew what I was talking about. And I said that this was basically weight decay. So when you say that I use regularization in deep learning, you mean that you use weight decay. Although I have found a paper that was claiming that the way how you use regularization is not how it seems or something like this. So they were claiming that weight decay and regularization are not the same things. But normally in community, when you say I use weight decay, it means that you use usually L2 regularization, usually, but could be something else. And we will discuss other methods that you can, regularization methods that you can use to regularize neural networks, okay? All right, so here's the Collaboratory. I'll send to Slack the link to Collaboratory just to remind you. So please go to Slack, because I'll probably send also the some pieces of code to Slack. So this is a link to Collaboratory. You should be able to just open it, and then you should be able to save it to your drive. That was the point. So you can't really edit cells in my version. Otherwise, we would have a chaos here. So you should be able to copy it to your own drive, and then we should be able to work with that. Okay, so this Collaboratory actually contains homework number 2, which deadline is June 4th. And I have, let me show you that. Okay, so I have actually opened the submission for homework number 2. So yesterday I opened the submission for homework. Actually, the day before yesterday, I opened the submission for homework number 1. And yesterday I opened the submission for homework number 2. By the way, I just wanted to remind you that you have a link to Collaboratory right here. So this is a regularization Collaboratory. This is supervised learning Collaboratory. This is slides for regularization lecture. These are slides for supervised learning lecture. These are slides for regularization information. I'll probably add a couple of words in the syllabus about homeworks, about deadlines and that kind of stuff. But basically it says that 4 homeworks, 25 points and that kind of things. Do you guys have questions about the website, the organization of materials, the homework deadlines, whatever you have? Okay, because, let me know, because at some point you will be left face to face with these challenges. And it's nice if you could, figure this out before challenges come out. Okay, so let's start with the first cell. We just set up as usual. We just do a setup. So we suppress some warnings. We load NumPy and we load pandas. I load OS just in case, I guess. I'm not sure I'm using it, but never hurts. I create example data. This is the same example data that we had before in the lecture. So the same 5 points. My perfectly looking ggplot2 code. I know many people love it. It's amazingly short, very concise, but also it produces nice point graphs. So I really love it. I'm really sorry for people who actually program in Python and they feel like this is torturing the language. Okay. So these are the same 5 points we had on the lecture slides. And now, so what we're going to do, we're going to first do a normal linear regression. And you probably remember the W1 formula, and you know that you need to, code it. So please code it here. So calculate the W1 for example data, but just remember that now we don't have distance and fair amount like we had yesterday, but now we have X and we have Y. So it's gonna be much shorter. It should look much shorter. So please do program this part, W1 equals, and then just enter your code. I have already pre-coded the intercept for you. So that should be easy. So W1, please add W1. And this is going to be a normal linear regression without any regularization, just pure linear regression. So I'll just give you a couple of minutes. Catch your breath, warm up. This is a just warm up for the rest of the practical session. So write up W1 formula. Otherwise, go back to my regularization slides or supervised learning slides. And remember that this was a covariance divided by variance. So covariance between X and Y divided by variance of X. And try to remember what did we go through yesterday and the day before yesterday. I'm really surprised that Igor is not online. This is heartbreaking. I have to tell him that this is a heartbreaking. Yeah, he was late yesterday as well, but gosh. Anyway, yeah. So finish that line. Maybe send it to Slack. Hey guys, once you finish, send the line to Slack so I can simply copy it.
It's better to send it to chat. Thanks.
Chat. Why?
Slack is not as easy.
Oh, Igor is here.
Yeah.
Yay, Igor is here. You don't have Slack, right?
Well, I have, but only on phone.
Oh, okay. Okay, then send it to chat, please. Right.
Thank you. Thanks.
It's good that you caught up with the beginning. So I was afraid that you will come a bit later, and then we will be somewhere down there, and you won't be able to catch up.
No.
Whew, that's a relief.
Thank you.
Oleg sent something. Okay, so Oleg actually sent it to Slack. So everybody send everything to chat, or send them to both Slack and chat, because Igor did not have access to Slack. But I'll thank you.
Send to both.
Okay, cool. So I'll thank you, Oleg. I just copied over here. I copied over here, and thank you very much. It actually works. So it's actually correct. Nice. 0.6, that's as it's supposed to be. So now we draw stuff. Nice. So this is the humdrum, basic linear regression, pure form, nothing else, nothing extra. And now what we shall do is we use scikit-learn library. We use lasso and ridge. So lasso and ridge, these are just basically constructs as linear regression. These are models. So please just initialize lasso and ridge regression right here. So these are the names of the models. You use the same template as a linear regression. So you can basically, in the ridge case, you can write ridge and just brackets. Kenneth, do you think you can guess what goes into the brackets? What goes inside the brackets?
Sorry, I'm just trying to get the code running and the exercise. For some reason, it's not happening. So I'm not.
Which one? Tell me.
The exercise.
The exercise. Oh, this one.
Yeah, I even copied and pasted Oleg just to see what's going on, but it's.
Can you share your screen? Can I?
Yeah.
Okay, go ahead. Okay. Intercept is not defined. So you deleted the intercept, right? Did you?
Oh, that's what I already go. Thank you very much.
Yeah, go ahead and just copy mine. Yeah, this one. No, this is a supervised, right? So this one. Just copy my version and yeah, you should be good. You should be good. Yeah, this one.
All right, there you go. Thanks very much.
Yeah, sure. You can stop sharing, and then I can basically take it out. Cool. Anybody else having troubles with that? You can see that Kenneth survived. I didn't bite. Nobody. There was no pressure, so you're absolutely free to say I'm having troubles here. It doesn't work, doesn't run, and then we'll just community help will come to your rescue. Semyon, does it work? Okay, Oleg, does it work? Oleg, unmute.
Oh, for Oleg, it works because he developed the code.
Yeah, but maybe he deleted the intercept and now he's like, oh, that doesn't work. But the simple fact that he developed the code for W1 doesn't mean he didn't delete the intercept, right? So, Igor, does it work for you?
Of course, because it was developed by Oleg. Yeah.
Oh yeah, sure. So Oleg has this quality stamp, right? That developed by Oleg. It should work.
Yep.
Elena, how are you doing? I just noticed that you joined.
Good. So I try to find what I need to type in this ridge regression inside. So.
Oh yeah. So coming back to my original question, thank you, Elena, for raising this up. Semyon, what do you think should go inside the brackets? Here we go. So what should go inside the brackets? So remember, what's the most important parameter of the regularization that we discussed yesterday?
Lambda.
We should put the regression itself, the formula and the lambda.
Yeah. Lambda and coefficients. Yeah.
So basically, this is the model itself. So it knows how to get coefficients. It doesn't know lambda. That's the only thing it lacks, right?
You mean what should we would put in AL and R?
what should we put when we initialize the regression here?
Yeah, so I think X and Y. No?
No, so when we train the model, then we need to use the X and Y. But when we initialize, the only thing we need is what is lambda. For example, look at this one. So this is what we do to initialize just a pure linear regression, right? We don't really say X and Y here. We will say X and Y right here when we fit. When we what people in scikit-learn mean by fit is basically train, right? So when we train, we need to say what are you training for, and what are you training to predict for, right? So this happens here. When we initialize linear regression, there is no coefficient that you need to add here. This is a scikit-learn function, so it will figure out all the coefficients W1 and intercept by itself, right? This was our manually constructed linear regression, so we had to calculate W1 and intercept by our own hands, right? By these hands. This thing does it automatically by running, I think, stochastic gradient descent under the hood. All right, so it actually uses stochastic gradient descent. So just what should I type here? Kenneth, what should I type here?
Well, I guess give it the values that it wants. Give it the intercepts and the lambdas. Give it the what it needs.
Okay, so I can see there is some confusion here.
Can I ask you a quick question? So when you say to initialize all three models, what does it mean initializing the model?
Okay, so what does it mean to initialize? No, it's a very, I think it makes sense. I see, guys, that you all have the same confusion. It makes sense because, so what we have done here was that we basically, let me show you this, okay? Let me just show you this. So what happens is that we, so this cell here is equivalent, okay? It's absolutely equivalent to the following. We take a linear regression. So first of all, we load the linear regression from scikit-learn linear model. So this is one line that we need. We load the linear regression, all right? Then what happens is that we initialize the model. So I'll just, I remember, Kenneth, about the question. I'll just show the cell, right? And then what we do, we just say LR feet, and then we say, hey, take the example data X as your X, and example data dot Y as my Y, right? So I can even say that this is this parameter, this is that parameter. I think X is capital. So basically, when I run this now, I will have inside my, right, so, okay, this has some trouble here because of some, maybe I shouldn't really use this.
I think Y is capital.
Y is capital. Oh, I think it shouldn't matter right now. Okay, let me see how okay, got it. So this is pandas stuff. So I actually need to write it like this. It's just another way to address the same, to address the same variables. It's the same stuff. All right, so I have a linear regression variable right now. This is an object. This object contains some attributes. Do you guys remember how do I look inside the object of the scikit-learn? We learned it yesterday. What was the function that I need to use?
Dot intercept, underscore intercept.
But what was the function to actually list all the attributes, all possible attributes?
LM
dir. It was a function named dir. Okay, so it would tell me all the possible attributes, and then Simon was saying that if you look at the intercept underscore, it will tell me what's the underscore, and hooray, the underscore is exactly the one that we calculated manually, right? If I look at the coef underscore, then it will give me the coefficients, the weights. So these are the weights, and we have just one weight, 0.6. And this is exactly the same 0.6 we just calculated manually. All right, so this cell here is equivalent to this cell here. It's just this one is done by these hands, by your guys' hands, and this one is done by scikit-learn people, okay? It's just the equivalent way to get the same results. So what they do in here, they just say that whatever will be, it will be a linear regression inside of it, okay? By initializing, I mean that we just create an empty instance of linear regression, all right? So Kenneth, tell me something. If I just initialize, so I just create an empty object and I'll put an empty object of linear regression inside of it. What happens if I check for a coefficient?
So this is where I'm not sure. So does it grab the data frame that's just in memory and works it off of that, or will this be empty? Will this be a null set?
It would be basically saying there is nothing in there,
So
one way or another. So
Okay.
it would be saying I have not trained. It says that I haven't trained on real data. I haven't seen the real data, so I couldn't really have the coefficient or whatsoever because I haven't seen real data. The same will happen to intercept. So if I try the intercept, yeah, you can't see that it doesn't know the name of it, and it will tell me I have no attribute intercept because it didn't learn, it didn't train. But as soon as I train, as soon as I write a lar.fit, and then I say, okay, use this one example data, and then X, and then please go ahead and just example data, and then here should go Y. So this is what I predict, right? If as soon as I do this, it will actually have the intercept and the coefficient. So this is basically when I run this line, I create an empty instance of linear regression. It's a naive and empty and clean. There's nothing else there. But as soon as I fit the function, I get some coefficients and intercept and that kind of things.
Okay, so it's kind of like doing like import, like you're just assigning linear regression to the LR.
Yeah, basically, yeah.
So all right, so there is no math happening by initializing. That's purely a programming.
No, it's just a programming. It's just saying here I will have my linear regression. There is this joke that when the programmer goes to sleep, they put a glass next to their bed just in case, even if they know they wouldn't drink it, they just put an empty glass there. So this is exactly what we do. We just put a glass, and then having this alar fit is actually pouring some water into the glass. All right. Okay. Any other questions? I actually thank you very much. This is important. I realized that we have this confusion in here. So again, this ridge, when I run this ridge, it's basically just saying, there is different types of glass. One type of glass will contain only linear regression. Then this is a type of glass that will have the ridge regression. And then this type of glass will have lasso regression. So what happens, what goes inside of these brackets? Igor, what goes inside of these brackets?
Well, I've searched the Google, so alpha goes there, then fit intercept, true or false goes there, normalize, true or false goes there, X.
Okay, this is like a lot of information now. So what they call alpha, I call lambda in this lecture, and in theory we call it lambda. So here is lambda. You can see it's called lumped. And do you know why it's called lumped, not lambda? Any guesses why I can't just have lambda like normal people would have?
Because
Olena, yeah, Igor?
Oh,
Sorry?
Sorry.
No, you were saying. Say it.
Because lambda is reserved word for
exactly. It's a reserved word, but so you can actually use lambda underscore if you want to have lambda, but I was using lumped just to make it shorter, and then you just put it in here. You just say lumped inside the ridge, okay, and that's gonna initialize the ridge regression with lambda equals to 1. So you can actually guess what happens for lasso. I'm just saying lasso, and then inside lasso, I'm just saying lumped, okay? Somebody may ask me a question, how do you think ridge knows that this is lambda, not something like what Igor has enlisted? He said that there are many things that can go inside. How does this function know that this is actually lambda?
Well, it's the only non-optional function. If you don't have lambda, then you're not doing anything.
I'm not sure actually. I think you can actually leave it empty. I think there's some default parameter.
But guys, you can use IntelliSense, yeah, this intelligent prompt. Just mouse hover the function and you will see all parameters which are expected from this.
Do I actually, if I hold the mouse, or I think it was basically if I, okay, the problem is I need to load it. I need to load it first. So if I would have a separate cell here, and if I would run it like this, then I would have all that kind of beautiful things that you said. So so it basically says that alpha is the first parameter, and by alpha they mean lambda. So whatever I put in, by the way, Kenneth, look at this. So alpha by default equals to 1. So if I wouldn't put anything, it would just say 1. So alpha lambda, whatever they call it, is the first parameter. So whatever you put in here and you don't specify the name, it will just use it. It will just think that this is alpha parameter. Okay. Okay, let's run this. Let's run this. Now the fitting. Right, so we now have 3 objects. They are completely empty. There's nothing in the world, like on the first day of creation. I'm sorry, there was no creation. But so you have these 3 models. They are absolutely empty. Ridge regression empty, lasso regression empty, no coefficients, nothing else. But here we actually create coefficients. So so basically, the process of creating coefficients for both functions is the same. For lasso and ridge, you just say, here's my x and here's my y. Here's my x and here's my y. That's all the same for both lasso and regression and ridge regressions.
May I ask a question?
Sure, go ahead.
Actually, yesterday we saw that lasso and ridge is good with polynomial. How do we establish, or how do we provide these polynomial parameters to the ridge and lasso? We just only provided lamp, which is
which is just the strength, right? How do we? So the question the question goes like this: how do we? So yesterday we saw that it actually makes sense to do some polynomial regression,
Yep.
But how do we actually tell ridge or lasso or linear regression that now we are working with polynomial regression? Just wait a sec. And we'll get into this, right? We will do polynomial regression right here in the collaboratory in like 5 minutes, okay? We'll just get into it. But thanks for asking. I love questions when they help me to lead the discussion. They're like front coming. They're like fortune telling. You know the fortune, you know the future. Let's just train the simple ones. So this is just using 1 x and 1 y. Right, so 1 variable, 1 independent variable, and 1 dependent variable. Here I was just saying, remember a function dir, okay? It was saying that here we have coefficients, here we have intercept, so these are the important things. And yeah, basically, could you write up, could you fill in these gaps? Could you print out the coefficients for ridge and lasso regression and in the appropriate places? Go ahead. Olena, how are you doing?
Good. I hope.
Where
so.
are you? Which cell are you on?
The same stage, so.
Okay, it's all good. You don't have problems. So, I mean, I cannot explain my question. I just don't see your face, so I don't know if
Okay, so
you're freaking out or you're like absolutely cool and everything is fine and you're like, oh, everything is okay. So you can just fill in these gaps here and print out the coefficients for ridge and lasso regression and see how they differ. See how they differ. Yeah, I'll give you just a minute to get this done.
I have to restart my runtime. I know.
Oh,
Catching up.
what happened? What happened?
It just froze. Just sat. Runtime not responding. So.
that's the worst part about collaboratory, is that it freezes sometimes and then you lose everything. Oh, well, fortunately, we didn't really go too fast, so you wouldn't need to, you know, catch up for half of the code. Would run half of the code. So I would just run I would run LR bridge, and then I would need to write coef underscore, right? So this is how you get the coefficients for the bridge. I think you all guys know that if I change this ridge into lasso, this is how I get the coefficients for lasso. So there is nothing new in here. Yeah, so if I write intercept underscore, then I will get intercept for ridge. And if I write LR lasso intercept, I'll get the intercept for lasso. Do you guys have the coefficients? So how the coefficients differ between the models?
Significantly.
Significantly. What's the p-value? No, it's just a joke, Simon. So whenever people are saying significantly, it means statistically significantly. It means that the p-value is less than 0.05.
P-value is invisible.
Invisible p-value. All right, so it's a hypothetically significant difference. Okay, Oleg, what is the most important thing that you know strikes you when you look at these coefficients? What is the main difference that you observe?
The main difference that for lasso, yeah, this coefficient is much less, yeah, than for each in linear regression.
Yeah, so ridge and lasso, they are harsh on W1, right? So they reduce W1. While the intercept, you can notice the intercept is growing. So I mean, they need to get the values from somewhere. So they increase the intercept and they decrease the W1 on the other hand. So they try to reduce the dependency between independent and dependent variable on W1, but they go a bit more flexible on intercept. Any questions regarding this? Okay, all good. Let's draw it. Let's draw. So currently we have only the humdrum linear regression, the one that we used to see yesterday and the day before yesterday. So now let's add the ridge regression was in red. So now the ridge regression will be in red. So here is ridge regression. And let's add lasso regression. Igor, do you think lasso regression will be more different than ridge from linear regression? Can't hear you.
Of course.
Of course. Why do you think so?
Because from coefficients we saw that lasso has intercept 3.7 and 0.1 as W1 value, so it will be like line.
Almost a flat line, right? Almost a flat line. You're absolutely correct. Absolutely correct. So it's almost a flat line here. Very good. I'm impressed. Thank you very much. This is good. A very good foreseeing abilities. So now coming back to your original question about polynomial regression, right? So this is what we do. What we do actually, we just add features into our original database. In the original database, let's recall it. We had this. So if I just type example data, you will see the original database. So this is our original database. We had X and Y. So what happens now is that we just take X and we take it into the power 2, and then to the power 3, and then to the power 4. And we add features. So let's do it. Let's do it together. So I'll just type example data, and then I can type X, and then I can say, well, to the power 2, right? So the same happens to the power 3
Power 4.
and power 4. Yeah, absolutely. Now, if you run this, you will see that now we have additional features, x squared, x cubic, and x to the power 4, right? Now, if we run, so now what happens is that we do nothing else. So everything else stays absolutely the same. Igor, everything else stays the same. We again just initialize the region lasso regression with the parameter lambda. For the linear regression, we say nothing. We just say linear regression. Just go ahead and grab the linear regression. It goes into scikit-learn storage space. It looks for a box with the name linear regression. It grabs the box, and that's it. All right. So let's do it. And now what happens is that we just take all these 3 models and we train it on the very same data. We take a very same data and we train it. All right. All 3 models trained on the same model, on the same data. And then we can output their coefficients. You can check out the coefficients. Olena, what do you see? What's the main thing that strikes your, that looks at you when you, that comes to your mind when you look at these coefficients? What is that comes to your mind when you look at these coefficients? What is it that is worth kind of mentioning when you look at these coefficients?
Like that we have 0 in lasso regression.
Yeah, so it got rid of, remember guys, yesterday we were discussing what the hell it did. Why did it actually get rid of the x and x squared? I don't know, but it got rid of these first 2 features. But we can also say that, well, for the ridge regression, the values are small. And for linear regression, the values are quite high, well, comparing to the other 2, right? What happens now is that there is a very complicated piece of coding happening. Just feel my problem, feel my pain. Why did I have to write all that stuff? The problem is when you visualize lines, you can just call a function called apeLine, which is just a way to make a line in ggplot. And in this apeLine, you can just say what is the slope and what is the intercept. The problem is when your model has when your line has more than one slope, meaning that you have more than one coefficient, you can't use this function. Can you guess what am I doing to visualize the line? To visualize less, not linear line, but like, you know, this kind of spline. What is it that I'm doing? What would you do if you wouldn't be able to, you know, use this nice function that uses intercept and coefficient because you got like tons of coefficients? What is it that you do? Any
Matrix.
What?
Matrix. Matrices.
Matrix? Is that what you mean? A matrix?
Yes, yes.
Oh, the one that we did yesterday. It's very close. It's very, very, very close. I do create a test set. So I do create a test set matrix, as you are saying. It's almost a matrix. It's a tensor. Well, it is. This one is a matrix. So this is true. And then I just predict. I take a row. And I try to predict a value for each of these rows using all 3 models that I have. This is basically I'm creating a test set for each of my models, but this is a synthetic test set, and you will see how why we need this test set. So here I'm just saying LR reach predict, and then each row in the test set. So I create, here is my prediction for my reach regression. And if I copy it in here, then this is my prediction by lasso model. And if I run this, you will see that now I have, for each row, I have a prediction from linear regression, from ridge regression, and from lasso regression. Now the question to the audience. What do you guys, why do you think I'm using these? What is the point?
I guess it's to drop dimensions onto graphable dimensions, you know?
Yeah. So I'll just use X dimension, and instead of drawing Y, I will draw one of these. So I'll just basically have points with coordinate X, and then the predicted coordinate by each of the regressions. And if I would draw them as points of the same color, they would form a line, because my axes, they change very, very smoothly, right? So I have a step of 0.1, 0. Plus 0.1, plus 0.1, and so on and so forth. So the step is very small, and I try to cover up the whole curve. So if I visualize this, then we will see something like that. Ask me questions about this. So the red one is rich.
Could you please copy this code snippet?
This one.
Yeah.
Okay, sure. Okay.
Just not to spend too much time.
Okay, sure. Okay. Did I cover up something else? No, I think it's all there.
Yeah,
so
overfit, crazy overfit.
Crazy overfit by the linear regression, right? So it's wrapping up the space as much as it's basically capable of. And then we have a red line, which is a red regression, and then we have a blue line, which is a lasso regression, right? Any questions about this? This is exactly what we have seen in the lecture slides yesterday.
I have a question about the TensorDB. Frankly speaking, I didn't understand the
purpose.
I understand. I see the result, but frankly speaking, I didn't understand this lin space formula. It splits on 61 steps.
Yeah. So basically, what it does, it just goes from 0 to 6 with a step. Well, actually, it doesn't really say a step. It just say this would be my start, this would be my stop, but in the middle, I should have 61 step.
Why 61?
Because this would result in 0.1 step.
Okay. Thank you. Now clear.
It's just I could have like 60, I could have 62. It doesn't really matter. It wouldn't change anything. It's just I really love that the step is 0.1, exactly 0.1. And I just calculated that if the stop is 6, including 6, then I need to have 61 step to have 0.1 step. I need 61 steps to have 1 step equal to 0.1. So this was calculated by me just, out of like thinking, okay, this is how much you need. More questions about this. Do you guys understand what's the purpose of this thing? It's just to visualize non-linear curves, because otherwise I wouldn't have the opportunity to see them.
Because there isn't a function that does this, so you have to hack one together, kind of a thing.
Kinda, yeah, kinda. Well, I couldn't find. So I just finished a course at UCU, at Ukrainian Catholic University, and people were constantly sending me much more elegant solutions and much more, simpler solutions to the problems that I had to hack. And they were like, you know what, man, this is just like this one function that you need, and that's it, and it's gonna work like super beautiful. So I constantly changing this code because I know I have a bunch of crap here, and yeah, so sorry for that.
But even without lin space, you can visualize this x and the y. But the graph will not be nice. I mean, it will be very much jumping.
Yeah. The problem is I don't want to just visualize x and y. I really want to project these lines on x and y, right? So this is the point that I'm trying to achieve, and that's been not very. So this is why I have a lot of crappy code that you don't like, and I don't like either. So. Let's not look into this because I'm getting embarrassed of my programming skills. Okay, but there is more to come. There is more to come of crappy code, more crappy code. So the crappy code here is just, so Kenneth yesterday corrected me, and he was absolutely right. So you don't say why to stop, but you say why stop. So I'm saying why stop, and we shouldn't stop. And we can go on to do different lambda, right, for ridge regression. So what happens if we use different lambda on ridge regression? And here we start with 0.1, and then we add 1,000. This is just for this is code for entertainment, just to you know, check it out. If so what happens here is that we initialize a bunch of ridge regressions with different lambda parameters, and then we train them. So we train them in parallel, ladies and gentlemen. This is very important. We are not training them. We are not training them at the same time. We are training them sequentially, one after another. And then we predict all the same test data that we have just discussed. And then we can obviously visualize them. So here we visualize them. So this is how it looks. The purple one is the 1,000. Sorry?
1,000? Sorry, I thought you were asking. I was answering your question. 1,000.
Yeah, so the purple one is 1,000. And the red one, the reddish one is the one with the lambda equal to 1. Right, so the most faint is the one that has 0.1. All right.
So why is it important that you run those sequentially?
No, it's just you can't really retrain on the. Basically, there is no other way. That's a very simple way to answer it. There is no other way. You gotta be training them sequentially because you can't run them in parallel. Because they train different models. So if you would be training the same model, you would be able to do it somehow otherwise. But since you're training different models, you gotta be training them sequentially in that sense.
But yeah, but sequentially from like low to high number, or just that?
Oh, it doesn't matter. It doesn't matter.
All right.
Yeah, it doesn't matter.
I thought you were saying the order was important.
Oh, no. So it doesn't really matter. I could have trained 1,000 first, and that wouldn't change anything.
Okay.
So yeah, just nothing really. Okay, so here I just look at the coefficients. I'm just looking at the coefficients, and you can see that the model with lambda equal to 1,000 is having very low W's. So the intercept is still quite significant. I don't have p-value to back this, but I'm just saying that it's quite high, while the weights are essentially very close to 0. Well, not super close in some cases, but they're pretty much low. Okay. One algorithm that I want to mention that makes sense to mention is called elastic net. Have you guys ever heard about elastic net?
No.
So in my practice, I have heard about elastic net, and I never had I never had a good understanding what elastic net is all about. In fact, elastic net is very simple algorithm. It's a linear regression with both L1 and L2 regularizations at the same time. So how does it work? You just add L1 term, and then you add L2 term, but you also balance them out by some coefficient. You can say, I want 0.5 of L1 term plus 0.5 of L2 term. Or you can say, I want 0.7 of L2 term, and I want 0.3 of L1 term. So you kind of have this ratio between L1 and L2 regularizations. And this is just what elastic net algorithm is. It's a linear regression with both L1 and L2 regularization. It just sounds almost like neural network, but it's not. So elastic net doesn't have anything to do with neural networks, okay? I have been confused for a long time myself. I don't want you to be confused. So elastic net doesn't have to do with neural networks. Let's just get this over our shoulders and move on to the next homework exercise. So homework exercise number 2 could be a bit more math involved. So this is something like Simone should be a happy person, should be happy about. So this is an exercise where I ask you to actually look into the closed form solutions. And let me explain what closed form solutions are first. Before that, we run the synthetic data generation. By the way, you need to We need pandas, and I guess make regression needs. I think we're lacking something. NumPy and the array. Okay, this could be my problem. This could be that it doesn't have the head. It could be that it just needs to type. Okay. Okay. X then 0 to 5. I don't know why did I have head there. I kind of felt that this should be a pandas array, but it wasn't pandas array. So you please correct this. It just type X. You can just delete the headline because it doesn't really make much sense, because it produces the NumPy array, doesn't really produce the pandas data frame. But what I wanted to do here is I wanted to make closed form solutions. So it turned out that what we have done for the linear regression for the case with one feature, it is called analytical solution for the case with one feature. So remember the one that we have coded ourselves here. This is so calculating W1 and intercept in a very specific, this specific way is called analytical solution for a feature, for one feature, for the case with one feature. And there is a closed form solution for multivariable, multivariate linear regression. So when you have more than one feature, you can still have a closed form solution, meaning formula to compute coefficients for each one of these features. And that one uses matrices. So you would need to use matrices. And you can also have closed form solution for a case when linear regression has L2 regularization. All right, so the exercise number 2 of the homework is about actually implementing a closed form solution for a linear regression and multivariate case, and for the ridge regression and multivariate case. So here I just create a synthetic data set that has 50 samples and 4 features. 4 features, 50 samples, okay? And here I ask you to look into this, to look here, Stack Overflow forum here, which says that I know that the regression solution without regularization term is this. And with a regularization, the closed form solution is this. So what I essentially asking you here is, can you please implement this in here, right? So can you please calculate, so beta, so these are the weights coefficients. So the question was, can you calculate weights from the closed form solution? Intercept can be calculated afterwards. So as soon as you're done with your coefficients, you can use coefficients as the same way we did to calculate intercept. Does it make sense, ladies and gentlemen? What am I asking here? Igor, you seem unimpressed, if I can make.
I love programming.
You love programming, you love math, right?
I will do my best.
You'll do your best.
Yeah, I wish I could be Oleg.
What's the difference between these forms? Closed form, the closed form solution.
So the closed form. So what scikit-learn does, when you look at the scikit-learn, it actually solves the stochastic gradient descent. So it does actually approximation. It approximates the solution while by optimizing the cost function. While in this case, you actually have an analytical solution. So you just calculate matrices, you multiply matrices in a certain way, and then you got your coefficients. And these are the mathematically perfect coefficients that you can get, right? So you just need to know the formula, and you need to implement the formula in order to get this kind of analytical result. While for stochastic gradient descent, you need to run this kind of optimization loop, and then you will approximate the result from this kind of optimization procedure. So that's the difference. Analytical.
So close is just means like a direct line path to the answer.
Yeah.
There's no iteration.
Yeah. So you get there like well, not in, so I can't really say it's instantaneous, because if you look at the solution, it got a couple of matrix multiplications, and matrix multiplications are not very fast. In fact, they are not fast. That's why scikit-learn uses those, is that they are not super fast. I mean, these days they're much faster than they used to be. If you think about matrix multiplication complexity, it's actually cubic. But nowadays we have quite optimized algorithms that do it in a kind of sub-quadratic complexity. So you get it fairly quickly, but still it may be it may take a while for large problems. So that's why I think scikit-learn uses optimization procedure. But otherwise, it's nice to know this closed form solutions. Okay. Right. So I'm getting back to, let me see, we have 20 minutes before the break. You guys can ask me questions in the meantime.
If I may, I'd like to ask the question about the homework. This matrix, can we use NumPy, or you want us to calculate to treat the matrix really manually, line by line, cell by cell? I mean,
no,
we'll use 4 or something.
I want you to use NumPy as much as possible. In fact, that's why I actually had this here, is that I actually wanted to go through this first half of this exercise by looking at this formula here. So let's take a look at this formula and let's try to do it together, so that Igor would have something to, you know, kind of to look at when he starts, and you guys all have some background here. So if I may, I just copy it in here. So this is the kind of solution that we saw on, sorry. Yeah, so t here multiplied by x into the power -1, right? Again times x, again times t. This one is to the power, and okay. So this is the thing. So this is the solution, right? This is the solution for LR coefficients problem. This is without regularization. So regularization is a separate thing. How do you do the transpose for the matrix? Okay, so we have a matrix X. So this is a matrix X. We can take a look at the shape. What do you think is the shape of X? Everybody, what's the shape of X?
54.
54. Exactly. What do you think will be the transpose version?
450.
What would the shape of the transposed X?
450.
450, yes. Okay, so this one is, I think it's like this. Yeah, sorry, we should have shape here. All right, so 450. Now a $100,000 question. So if I look at the, I'm kidding, I won't give you $100,000. It's just, so the question is, when I multiply matrices, I multiply one matrix by another matrix, what would be the final shape of the, first of all, can I multiply x by xt? Can I multiply x by xt right now? Or should I multiply xt by x?
Xt by x.
Xt by x. Can I still multiply x by xt?
Yes.
Yeah, it actually both ways. What is the important condition that should hold in order for me to actually multiply one matrix by another matrix?
This rotation rule, when number of rows, I think in the first matrix.
So number of rows here, and
shall match number of columns in the second.
Okay, this one. Actually, in fact, it's the other way around. It's the number of columns in the first matrix should match the number of rows in the second matrix.
Okay.
So these two values should be the same. If you plot the shapes one by one, like side by side like this, if these numbers match, you can multiply the matrices. And the resulting matrix would be of shape 50-50. So just the first one and the last one. So if I multiply it right now, I get 50 by 50. Okay. You may ask you may ask me a question. Why am I telling you this? It would make sense when you start multiplying, because you will get all this kind of weird problems. So let me just show you the shape. So this is 50-50, right? So this is the resulting shape of this matrix multiplication. So this is this part, okay? Now in NumPy, there is a function called inverse. I think it's called inverse. I'm not sure. That's invert. Oh, invert. Okay. So if I now invert these matrices, it should still stay 50-50, or okay, no, something wrong, something happened. Not supported the input types. Okay, let me check just a second, just to make sure that I'm not messing up with you and I'm saying something meaningful. Oh, okay, so this is, I just actually, I wanted to use something else. I wanted to use some other function. Let me see which one. Okay, so let me share the screen again. So I actually wanted to use not the invert, but NP linalc invert. So this one. Saying, I think I got too many brackets here and there. Okay, shape. All right, so this is again 50-50. What the invert does, ladies and gentlemen, what invert does. Simeon, what does invert do?
Around the central diagonal. Main diagonal.
So looks at the central diagonal, wraps around the central diagonal. So this part, so this thing is until here, right? Igor, what should I do now? What happens now? So I got this part right. Now I should multiply this by x to the power t. Can you tell me what happens? What should I add here? So this is highlighted right now, is what highlighted here. What should I do now?
I think coding, yeah.
Programming, yeah, absolutely. Python. So what should I add here?
You should make this multiplication x to the power t.
So I do math move, right? This is how I multiply the matrices, and then xt, right? So this would be the okay. This is okay. This is what I'm saying, that there could be a problem here. So what should we do when we have that kind of problem? There is some kind of mismatch. We look at the, we know that this one is 50-50, right? We know that xt is 450. Ladies and gentlemen, look at this one. I have, so let me post it in here. Okay, so here. I have this one with the shape. I have 50-50 times 450. What should I do? Kenneth, what should I do? This line to work.
You need to match them. So you either transform one matrix, either one up or one down.
What do you mean? What should I do? Exactly. What should I do? Simon, what should I do? Can you help?
Invert the other one too.
Yeah, but I'm kind of afraid of inverting things. What if I don't want to invert stuff? Igor, what should I do?
Don't know. Really have no idea.
Guess. What are the options?
Power -1.
What?
Power -1.
What if I do something simpler? What if I just change the order of multiplication? What if I multiply this one by this one? What if I multiply 4 by 50 by 50, 50? This one's to match. So I get 4 times 50, right?
That would work.
That would work. Let's give it a try.
I like how it's a simple answer.
Okay, let's see. Let's see if it works. Okay, I got something. Okay, so let me see what I got. It should be 450. Okay, this is 450. Now I have to multiply it by y. So what is my y? What is y? So if I go for y, it should be this. All right, so I have y, and then if I go for shape, I got just 50. So it's 50 times 1. What if ladies and gentlemen, what happens if I multiply the result of the previous operation, this one, I multiplied like this. Would it work? Ladies and gentlemen, would it work? What would be the resulting shape? Kenneth, what is the resulting shape of this?
I'm unsure. I was trying to catch up with your code. I was writing down code while you were talking.
Oh, don't worry about this. I'll just copy paste it into Slack. So you don't need to. Don't worry about this. So what would be the resulting shape when I multiply 450 times 51? What are the things that will be gone? What are the things that will be gone?
4-1 will be the shape.
4-1.
Yeah, 4-1 will be the shape, right? Because these 50 they will be gone.
Right. Yeah.
So if I do it right now, so I basically have to multiply whatever I had here. I need to write this math move, which is annoying, but yeah. And then I multiply by y. So this is what I get. Okay, these are the coefficients. These are the final coefficients that I get. Okay. So I just put it in here. And in the meantime, you guys, I could just copy it over. This is how you look at the shapes. I think it makes sense to check it out. Okay, this is looking at shapes. And this is the, let me just check it for a second, just to make sure that I'm, yeah, it looks like this is all right. XDX, XDX, yeah, sounds okay. Google Chrome. Okay, so I'll just copy this one over to Slack. Okay. All right, then you would be able to get the intercept and all the other things. Okay. So this was just to give you an impression of what kind of stuff I'm looking at this exercise.
Can you copy over the formula?
Sorry?
Can you copy over the formula, the text box with the formula?
Oh, but you have a link here. A link has a blog post with both formulas, so you can.
I know that. Just like you had to do formatting to make it appear correct, and it just says.
Yeah, I just did some couple of things, but I didn't really do much, so I'll just copy it in here. Let me copy it as well to the chat, just to for everybody to have it as well. All right, Igor, I also copied it to chat just in case. All right, let's get back to slides. Let us get back to slides. Okay, here we are. So the next thing that I promised was the weight decay. So from the last time, we didn't have the neural networks, unfortunately. This was a lecture that I had to skip. But essentially, the idea is like this. We have a point that has coordinate x and y. And what happens is that we predict the class of this point. So we predict either class purple or class blue, right? We have this very simplistic neural network that have one hidden layer with 2 neurons. These neurons have a sigmoidal activation function, and it has two output neurons that predict the class scores. So what is the score of the class purple, and what is the score of class blue? All right, this is actually reddish. Okay, so this is class 1 is reddish, and this is purple, the class purple. This network also has biases. So this is bias number 1, this is bias number 2, and it also has weights. So all these weights, W1, W2, W3, W4, and so on and so forth. These are the weights of the model. This model is optimizing MSE, mean squared error, right? So it tries to make sure that the class scores are as close to the target class scores as possible by optimizing MSE error. I'm not here, I don't want to explain deep learning. So I just wanted to explain one single part of applying this L2 regularization and L1 regularization to deep learning. So during the feed forward, we just add the L2 penalty, L1 or L2 penalty to the MSE. So besides MSE, which is the error that we know how to compute, this is the mean squared error. We look at the each of the differences with the targets, and then we compute the average of squares. We also add this square of sum of weights, right? So sum of squared weights and times lambda, of course. So this W here is actually each one of the weights that we have in the network, right? So we have eight weights, so we basically have a sum of 8 squares, right? Yeah, that's pretty much what happens during the feed forward path. So when we compute the class scores, this is what happens. We just add to the error this L2 or L1 regularization term. This is, Igor, is that L2 or this is L1? Here. I can't hear you, can't hear you.
L2, L1 without powers.
Great, gotcha. Now the important question is what happens when we do back propagation, right? The stuff we discussed yesterday. The full back propagation for this network, for example, we want to, again, we didn't have it last time. So we have a MSE. This is how you calculate the back propagation for the weight W5, right? So for the weight W5, when you look at the, basically, if you want to try to compute the gradient with respect to W5, this is the MSE of this term. But now we need to also backpropagate into L2 penalty, right? So when we want to know, if we go back to the network here, we want to know how much the MSE error is influenced by W5, how much this weight influences the total error, all right? And in order to do that, we calculate the gradient. So the gradient of this influence of W5 is this horrible formula that I won't even try to explain. But in fact, this formula is just basically saying how W5 is influencing the MSE, right? So we have a total error that consists of MSE plus the regularization term. First, we need to figure out how the W5 influences the MSE. And then secondly, we need to figure out how W5 influences the L2 penalty, okay? There are two terms in the error, MSE and penalty. First one computes the error with respect to MSE, and second one computes the error with respect to penalty. So since the penalty, the penalty is like this, is basically a sum of squares. We substituted instead of the formula. So look at this. We have the dL2 penalty divided by dW5. So this is a partial derivative with respect to W5. We substitute the sum here. Okay, this is the same L2 penalty sum. When we write it, so yeah, the lambda term is not important because lambda term does not depend on W5, right? So we can just leave it out. We can get it out of the brackets. And now we can just write out the sum. And then we can write it out even more. Oleg, can you tell me what's the result of this horrific a mathematical expression. So when you have dw1, 2, 3, 4, and so on and so forth divided by dw5. When you take a partial derivative or whatever is in here by w5, what happens? Simon, what happens?
All the w except w5 are constants, so we will have zeros instead of those w's. And
Gotcha.
w5.
And what happens to w5, Elena? What happens to w5? What happens to this term? Dx squared times dx.
This shall be 2 power. This is a multiplication, yeah. No, not multiplication. So we need this power multiple as value, yeah. It will be 2 multiple by. Is it correct?
Okay. Yeah. So 2 multiplied by what?
By derivative w5 and derivative w5.
When you take when you have x squared and you take the derivative with respect to x of x squared, what will be the result?
2x.
2x. So if you, instead of x, you have w5.
2w5. Yeah.
2w5, of course. This is the result. Easy peasy lemon squeezy, right? And so you have basically lambda times 2 times w5. And then most of the time, people actually use here term 1 over 2 to get rid of the 2 as well. So people actually get rid of the 2 here as well, not to have weird stuff hanging around. So all you need to know about backpropagation with respect to when you use L2 regularization is that to the overall backpropagation that is happening anyway, you just need to add lambda times w5. And this is anyway done by the backpropagation algorithm. When in Keras, you add weight decay, and we will see how does it work. So this is what L2 regularization term, this is how L2 regularization term looks like. How about L1 regularization, right? What about Lasso?
Sorry, could you please remind what is the backpropagation? To be honest,
Didn't guys study backpropagation algorithm?
Yeah, no, we did. Yeah.
Yes, we did, but let's say.
I was
not yet finished. Yeah.
I was. Oh yeah, sorry. This is a okay. Now it's a break. You know what? I love to give you a talk about backpropagation. So if today we will be on time, and we will finish this lecture, I hope we can actually go through the backpropagation, because you can't really say with a couple of words what backpropagation algorithm is. I have like 200 slides about what backpropagation is. I do realize that this was a silly part of me. I just was like, oh, I assume you know what that backpropagation is. That's not the way how you do business. Let's do it like this. Let's try to finish it as soon as possible. There's a little left on regularization lecture. As soon as we're done, I promise you to give you a little bit about backpropagation. Okay? Is that fine?
It's fine for me. What's about other guys? I don't know. Maybe.
Other guys. Okay, other guys. Yeah, since Elena, you're missing out on the democracy part here. There's a democracy in here. So what's your say?
I'm fine, so we can do this.
Fine. Gosh. I feel for you. All right. Anyway, have a break and let's get back at 10:33. Okay. See ya in 10 minutes. Oleg, I'm really sorry for. No, I was just saying that I'm really sorry that I kind of jumped it over and said, oh, you know what backpropagation is, and just I hope that we can manage to get through some backpropagation slides today and recap. Kenneth, I can't hear you.
So, I mean, to what degree do we need to understand backpropagation? So backpropagation, by my understanding, is tuning the iterations of the neural net by changing the values from the result of that thing. Does that?
Yeah, that's the right thing. That's
yeah, but do we need to know in much more detail than that in order, or is that?
It depends. Depends for what. I think your intuition is correct. That's what, on a high level, what backpropagation does, but it doesn't explain how exactly it does it. So I have an example why exactly this way, and yeah. So in a sense, I think your intuition is perfectly fine. Yeah.
Yeah. Okay. Because I mean, we studied it, but I've retained the high level understanding, not the
got it. Yeah, it just how do you get this? How exactly you change the weights with respect to what? How do you calculate this change? How do you know by how much you need to change? Right, that's the most important question. Yeah, that's the.
And that's because it influences how you would choose lambdas when you're doing. Understanding that gives you better accuracy in what?
This is important when you select an architecture, when you think about the architecture of deep learning, when you think about these activation functions for each of your layers, when you think about the sequence of your layers, when you think about why it doesn't work. For example, when you see that your backpropagation, it's not about backpropagation, it's about your training. When you see that your training doesn't work and it's stuck somewhere, or it just doesn't really do a thing, then you may be able to come up with the reasons, with explanations why it doesn't work. It's all about why do we have vanishing gradients problem, for example. If you heard about vanishing gradients problem, then it explains what vanishing gradients problem is and how can you avoid this problem. Yeah, that kind of stuff.
Okay, that's good. All right, that's good to know. Thank you. I'm gonna make a coffee now.
Go ahead. Me too.